是他们的 OK。哎，你们review要换什么？因为李安者已经报告3次，所以系统已经把它disable掉了。好，那你们去重新写一次。好，没问题，给他们确定。
Hello, honorable judges and contestants. This is the reporter Xu from Team MD Joker, and today I'm going to present problem number 11, spring hysteresis. And this is an outline of my presentation. This is a bond statement. Connect two identical linear springs symmetrically to a mass in a V shape and apply an adjustable force to the mass. When this force is varied, the resulting motion of the mass depends on the history of changes in the applied force under certain conditions. Investigate this phenomenon. And our main focus on this problem is the adjustable force, the motion of mass, which we think is the position over time, and also the history of changes in the applied force. And this is a demonstration video. So here, in these two different directions of pulling the mass, we can see that at a particular position and force, the spring will be highly compressed and the mass will be pushed to the other side in a very short time. However, we can see that the bending of the bending of the spring is easily observed, and this will be discussed later in our experiment discussion. And this is our experiment setup. So use a wireless force sensor to calculate the force that is given to the mass. And also the plastic board over here is used for constraining the motion in the 2D plane. And here comes our theory. So first, we want to analyze the force on the mass. And because the mass is in the middle, we're only talking about the vertical components of the total force. So the total force in the vertical direction can be expressed using this equation. This is the force from the two springs, and this is the external force. And here we include the gravity of the mass into the little f, which is the force. And from this equation, which we call equation 1, so we put it into the graph. So if we have the graph of equation 1, when L0, which is the natural length of the spring, is smaller than x, which is the distance over here, the graph will look like this. And if L0 is bigger than x, the graph will look like this. And because of the different points of the graph, we only talk about the hysteresis phenomenon when L0 is bigger than x. And the hysteresis phenomenon only happens when in this situation. And now we want to consider the value of y star, which we define, so that the function of y star equals to 0, which means the value of this one is equal to this point. And these two are the graph, and we assume that the external force is 0. So the meaning of these values is stable points of the mass, which means it reaches equilibrium in the total external force. And here we can see that there is only one value of y star in this condition, and there are three values of y star for the other condition. And this is also why the hysteresis phenomenon only happens in this condition. And after we can know that the hysteresis phenomenon only happens the natural length is bigger than x, we can try to calculate the local minimum and local maximum of the function of y, which is this part and this part. And this is how we calculate the local minimum and local maximum that we can calculate over here. And regarding the values of the little f, which is the total external force here, we can see that this is only this vertical shift of the graph. So at these two values, which we assume that this is f equals f2 and f equals f1, there are actually only two values of y star, meaning that one of the former two values are overlapped together at this point and this point. One as a local minimum and one as a local maximum. And this means that it is not a stable point anymore. It is a point when the total force is 0, but it still has a velocity. So we want to calculate the values of f1 and f2. So we substitute f1 and f2 into these equations. We can get that f1 equals the negative f2, meaning that f1 and f2 are only different in the direction, which is upwards and downwards. And the magnitude of f1 and f2 are all the same, and can be expressed using this equation. So if we plot y star to the value of f, we can get the hysteresis curve. And this means that there are two variable paths for changing our f. So the first is the purple path, which is from lower than f1 to f2. So when we start to add the value of f over here, gradually, when we touch it, the value of f2, the hysteresis phenomenon will happen, and then the spring will be pushed to the other side in a short interval, very quickly. And for the blue path, which is the second variable path, if we start from a very big f, and then gradually decrease the value of f to f1, then the hysteresis phenomenon will also happen. And these four different little pictures show the different conditions in the position and the direction of f. And here comes our experiment. So in the first experiment, because we only have the same natural length of the springs, so we have to make sure that the force of each the force acting on each spring doesn't exceed the elastic fatigue. So we calculated and measured the critical value of maximum extension, which is 0.083 meters. And this is experiment data for different types of our springs. And the natural length of each spring is always 0.1 meters. And this is our second experiment, which we're going to change the spring constant. And we also control the natural length of L0. And here we want to find the value of F1 and F2, which is where the hysteresis phenomenon happens. And we can see that according to our theoretical equation, we can get this proportional line. And we can also see that our experiment data fits the theoretical line, and the error is within the range of below 9% margin error. And next is our third experiment, in which we are going to change the horizontal distance x, which is this distance over here, and from 0.02 meters to 0.045 meters. And the reason we only do to this value is because if x is larger than the natural length of the spring, the hysteresis phenomenon will not happen. And here's our results. So we can see that even though for 0.035, 0.04, 0.045, and also 0.03, they fit the theory line. We see that there's an obvious deviation over here in 0.02 and 0.025. And the trend of our experimental data and the theoretical line are all the same. However, we want to know what happens for these two values. And we know that the bending of the spring is actually very significant in these two values to cause this deviation. So yeah, this is the bending of the spring. So in our theory, we assume that the spring won't bend and it will only compress and extend. So in our theory, the condition should be like a straight line for the spring, like a V shape and a V shape. But however, if it is bending, it will cause the loss in the force. So this is why it will cause a deviation. And so after we have this this picture, we want to bend the spring to with the force sensor to actually know how much difference there is between the bending of the spring and only compressing the spring. And we get these values. And after we add these values to our experiment data, what is the difference? We can get the we can see that our experiment data fit our theoretical line after adding these two values. So this, and there is only lower than 5% margin of error, and after the difference is added back. So we can still prove that our theory is correct. And at last, we put the whole motion into tracker and track the displacement in the vertical direction over time. And we also plotted the horizontal as the magnitude of, horizontal coordinate is F, and then the vertical coordinate is the position, the Y. And sorry, I didn't mention this. And these are for different horizontal distance X over here. So we can see that this also fits what we predicted in our theory, because if the X is bigger, then it means that the magnitude of F1 and F2 are smaller. So it means that the width of these two vertical lines will decrease with a larger X. And here comes the conclusion. So in our theory, the hysteresis phenomenon only happens when the natural length of the spring is bigger than the horizontal distance X. And the gravity of the object is included in the external force, little f over here. And the bifurcation, like the hysteresis diagram, and the hysteresis phenomenon happens when f equals f1 and f2. And this is the conclusion for our experiment. The magnitude of f and the spring constant k are positively proportional from these range of data we did. And the magnitude of f and horizontal distance x are negatively correlated. And we also discovered that the bending of the spring is a major factor that causes the experiment error. And after calculation of the difference of force to the bending and only compressing. After we add back this value, we can see that the experiment data still fits our theory. And also the width of the hysteresis curve, which means the magnitude of F1 and F2 are shorter when the horizontal distance x is bigger. And this is the end of my report. Thank you.
Oh, that's it.
Okay, thanks for your report. So can you please turn to the page? So you let experience distance lay on the table, right?
No, it is in the vertical plane.
Okay, and so can you explain why the spring doesn't snap back to its starting point right away?
To its starting point?
Yes, here. Why? Why you won't snap back to there right away?
Because of this graph, because in this part, the spring will be snapped back. So we need to add our force until this value or this value to let it transfer into this stage, which is when the spring will snap back.
So how will you predict the shape of the springs from your formula? The shape. Like this.
Oh, so we assume that the spring is always a straight line and will not be bended. This is our assumption in our series.
Okay, so did you change the springs every time you end the experiment?
Sorry?
Change the spring.
Yes, we do.
Okay, so did you put the experiment data into your formula to make sure your formula is right?
Yeah, we do have a theoretical line from our formula, and then this is our experiment data.
Okay, so what does the force tensor do?
It measures the force I'm applying,
So
the magnitude of the force I'm applying.
okay, thank you.
你的心态所
chain division, and yes, here's the problem statement. So the main focus is inhibition, and we can apply force on the central condition and investigate this phenomenon. So the reporter, the theory and experiment is they have the process to explain the experiment by the formula or something else, and the experiment is set out clearly, but I think the passive blocker will affect the fusion conditions. So let's talk about next data. So, and they describe how F1 to F2 in the page can detailed. And the experiment, their setup is they use force sensor to control the force they input, and they do the parameters like the distance of the string, or L0, or X and K. And the result is when L0 is bigger than X, it will happen. This phenomenon will happen. And the next, the strength of the report is that they make the audience got to get to know the experience. And the second one, they put a lot of trust and data to us to know clearly, and they use the experience data to make sure the formula is right. So, but I suggest them to record and talk about the 2 in 2D world, not the 3D world. So I asked them, can you explain why the spring doesn't snap back to its starting point right away? So the report says the springs are always stressed. And the second question is, how will you predict the shape of that series block with the formulas you have? So their answer is they model with the formula. Just from the formula, you can predict the shape of it. And the third question, and the next question, do you put data into the formula to support the experiment? And the reporters say yes. And now I cannot invite the reporter to. So can you please turn to page 7? So can you explain the meaning of this formula?
Yes, so in this stage, because we know that only this kind of curve will happen the hysteresis phenomenon. So we want to find at this point where is F1 and at this point where is F2. These 2 points are the points that will happen at the instant that the hysteresis phenomenon happen. And this is the process of the mass being snapped to the other side. So we want to find the values of this point and this point. And this is how we calculate it.
Okay,
and these are the results.
So can you tell us the units of the formula? The units of the value of X and Y.
Yeah, so X, the unit of X is meters, and the unit of Y is also meters. Yeah.
And
it's only the SI unit.
Okay. Can you please turn to page 12? So why the trend will suddenly go down? Why?
Oh, because here is elastic fatigue of the spring. Because when you extend it too much, you have elastic fatigue. Do you know what elastic fatigue means?
Yes.
Yes, so this is where it happens, elastic fatigue.
So is the formula predicted? Use the formula to predict, or is just an experiment?
This is my experiment data.
Okay. So the next question. So can you please turn to page 21? So can you explain these figures? What's the meaning of these figures for each one?
Yeah, so these 6 figures are trying to show the hysteresis curve because this is what the power standard plots. And I'm sorry that I didn't label the vertical graph, the vertical coordinate and horizontal coordinate. So the horizontal coordinate means the little f, which is the force, and it is the unit of it is in newtons. And the vertical graph is y, which is a position. And so if we plot the position to the force, we can get the hysteresis curve according to our experiment.
So
and these 6 pictures show the different hysteresis curve for different x. Yes.
So the next question is, do you think that if we change the spring to the sinking, will this not happen or not? If we change the springs to the sinking.
To the sinking?
Sinking, yes.
So okay, I don't know why you asked this question because the problem statement said a spring, but I think that if we change it into a slinky, because a slinky cannot be compressed, so it will not happen.
So, can we change your shows your experience out?
Here?
Yes. So you guys use the force sensor, right?
Yes.
So do you guys use the force by human hands or the machine?
By using the force sensor to attach it to the string and use the string to pull it, and we use our hand to pull the force sensor.
So will that have any errors if you use your hand or not?
Yes, it will have, but I think that by using a force sensor, it is measuring the force of the string. So I think that this doesn't have a very large effect on our results.
So what's the passive force to the string?
Yeah, so we attach the spring into a wooden board. And then because we want to constrain the motion of this mass in the vertical direction, not this direction. So we have to use a plastic board to sort of make it in this plane, make the motion in this plane.
So the spring surface will touch the passive board or the wooden board?
The wooden board.
The wooden board. So do you think the results will affect by the friction between each?
Yes, and I think that this is included in our error.
It's included in our error?
Yeah, this is one of the factors of the error.
So what will you do to reduce this error?
I think that there is no actual need to reduce this kind of human error because we can see that from our results, the error range is only plus or negative 9% for every data. This is within the range of 9%. So I think that except for bending, we don't actually have to try to calculate. Correct this error. I think that bending is still the most significant error in my experiment. So that will cause a deviation after this experiment.
So you say you can predict the shape of the by your formula and right?
The shape of what?
Screen. D shape.
No. The shape of the spring.
Yes.
But the shape of the spring is line.
But can you please the result of the experiment? They have the picture.
You mean this page?
No.
Which page do you want? Can you tell me the number? Page number?
Can you please complete?
Oh, okay.
And it's not a line. It's not straight. So
Yeah, because in our theory we assume that the spring will not bend. It is always a line, and that is why the theory says that it should be in a V shape because it is always a line, right? But in reality, we can't control the bending of the spring because the spring will bend, and this is also what we think caused the error over here.
So do you think the length of the spring will change?
Yes, the length of the spring will change. It will be compressed.
So do you think? So do you think the springs will have the V shape or they have another shape of it?
Can you say again? I don't really get what about that.
So do you think the springs will only have the V shape during the experience, or they will have another or other shape of the spring?
So in my experiment, I observed that the spring will bend, so it will not always be in the V shape.
Okay.
The V shape is only in the assumption that the spring will not bend.
So do you think you should have the hysteresis? Do you think they only have? Do you think it only happens when the springs has V-shape or?
No, in our experiment, even though the spring is bending, we can still observe the hysteresis phenomenon. But
So
the bend on the spring only contributes to the deviation between our experiments.
So do you think this other shape will still have this kind of?
What do you mean by other shape? V shape?
You. It's a V-shape, right?
Yes.
So what is your?
This situation will only happen in the middle of the hysteresis phenomenon because when we reach like a certain value of the little f, then it will not stay in the middle because this is a stable equilibrium point. So when it is in this situation, it will have a velocity upwards, and this is actually and this you said this situation is actually the situation at the origin of this point.
Okay, so it's only happens when x and when y is equals to 0.
Yes.
And here's all my questions.
Okay, thank you.
And here is the discussion between me and the reporter. So I extend formula use or experience data and back to prove the formula is the experiment data and the third is why the line in the neutron will suddenly decrease and the fourth is the thinking. They tell us the thinking isn't a spring, so they didn't do experiment and the purpose statement isn't talking about the thinking. So I asked them if they use hand or not, they say yes. And I asked them what is the passive stage4 do, and the answer is that to touch the wooden boards and what shape of spring it is, I asked them. So here's my discussions.
Okay, so it's my turn. So for your opponent, do you think the reporter consider motion because the problem statement is motion?
Which motion?
Motion of the mass, obviously.
No.
So do you think you consider the motion of the mass?
Yes, in the hysteresis curve.
Oh, so how fast do you pull the mass?
Position.
How fast do you pull a mass? Because the motion has a velocity, the acceleration. And why is it? Do you present
in our definition of motion, it means that the time is, the motion means that the hysteresis phenomenon, which is when the mass is pushed back to the other side.
Okay, do you agree? Yes. Oh, sure. Okay. About the spring, you said that there's bending, right?
Yes.
So what's the direction of the bending spring? The force?
The force of the bending spring?
Yes, because it's bending, you can't say the force
Well,
is
the
linear.
direction has to depend on how it bends.
So you consider all the situations in the motion, all of them.
Yeah, we only observe it from what we see in our experiment.
So I
So we can
see.
try to calculate the difference between.
Okay, I see you using a force sensor to pull a spring, right? And do you think that is what happens in the hysteresis system with the mass, then just pulling in a force sensor? Is that the same?
Yes.
Okay. So, what do you think? You think to avoid the spring for bending because there's a lot of errors in the experiment. I've seen that 9% of error, right?
Yeah, less than 9%.
Oh, so any option to fix that?
Yeah, so we did this correction, so see that the difference of the force between bending and only compressing.
Oh, sure. Okay, so do you think that the error is acceptable? The 5%, 9%?
No, I don't think so.
Then what do you think is acceptable?
Around 3%.
Oh, sure. I know you're right. Okay, so do you sure that the force pulling the mass is always vertical, not horizontal or
In our experiment, if we observe that the angle between the line and the vertical is more than 5 degrees, then we won't use this data.
Oh, so yes or no, you have only vertical.
Yes.
Do you think this is possible?
Yes.
Well, we try to control it in the vertical.
Okay.
And if it is more than 5 degrees out of vertical, then we won't use this data.
Fine, I think that's all.
Okay. Review the text on the floor.
Okay, I'm a reviewer of Lagrange, and this is the problem statement that they should really consider: motion. Okay, so reporter says very force dynamic motion. Okay, and no focus on mass. And opponent have the agree on put too much on the space and did not notice the inconsistency of statement. Did not focus on the motion. So this is the pros and cons to a reporter. We can see the pros consist explanations on static equilibrium, elastic figure considered, and the consideration of different springs. No varied force. Theory equilibrium only explains statics and motion effect on hysteresis unclear. No confused bending with buckling. You see, buckling, bending. Okay, and no velocity time graph, no acceleration and time graph. Something like that, intention done, and experiment on low speed and replace the quasi-static case. And this should be a motion. You can see acceleration and velocity, but no consider of both reporter and opponent. This is the pros and cons to an opponent. We can see cons. Discussion not deep enough. Should determine reporter's faults and did not help with the understanding with the problem statement, which includes motion. Depends on the reporter. I don't know why. Okay, this is the question and answer. The question: why the spring does not slack back? And the opponent says, reporter says always straight. And question and answer, you can see the shape by the theory, and there's only an answer of by use bending and the spring geometry to explain. And I don't think that's correct because the direction of force should be changed, and of course buckling. And here hysteresis curve meaning get curves with force and displacement. Okay, that's correct. Okay, but quasi-static, no motion. Okay, so change of slinky, I don't know why, but slinky cannot be in hysteresis because, of course, not pushing. There's no hysteresis, so it cannot be compressed, of course. Okay, human head or not. So So the answer of the request is force string to sensor. I think the vertical is okay, but I don't know what. They should try some pulley or something else. Okay, so the effect of the string unclear. A machine will be working better. You can see that. The shape of the spring assumes spring would not be bent. Of course, now you can see the picture, and that's buckling, of course. Did you consider the motion? And no, and no. And of course, problem statement says motion, so velocity should be considered also. And error acceptable, the opponent says no, it should be smaller than 3%, and the reverser says yes, but I think that's already too big. The horizontal motion, the reverser says there's only horizontal motion, and the opponent did not agree. That's all, and I want to suggest you guys to consider this shape, a solver of shape. You can see it only has vertical, and it won't bend. And also, it won't pop out of the dimension by using the board. So I think it can solve all of your problems by only this device. That's all.
Now it's time for Jimmy to ask a question. Sorry, I forgot. As a concluding remark for the remote.
This is a concluding remark on the report. So, the concluding remark for our presentation. In our presentation, we state that the hysteresis phenomenon only happens when the natural length of the spring is larger than x. And the bending of the spring is a major factor of our experiment error. And bending is more significant for smaller x. And the width of hysteresis curves and horizontal distance x are negatively correlated. And it is because the magnitude of F1 and F2 are negatively correlated to x. And for discussion, the plastic board seems to limit the motion of mass in the vertical plane. And I think that the reviewer gave us a pretty good suggestion on how to improve in our device, but we don't have the things they use. So I think that maybe we can improve it in future experiments. And we make sure that we put the string in the vertical direction. So if it is more than 5 degrees from the vertical direction, we won't take that into account. And this is why how we measure our experiment data. And the bending of the spring is a major factor of the experiment error. We think that the friction of the board doesn't actually affect a lot. And we think that the motion of the mass should be defined as a position for different force. And this is why the hysteresis curve is generated, not only by the velocity to time graph. And we actually, when we plot the position to force graph, when we plot the graph, it is the overlap of the graph of velocity over time and the force over time. So we still think that we can, it still shows the hysteresis phenomenon. And thank you. This is all.
Sorry, my previous mistake. So now it's a real time for Jimmy to ask a question. Professor Sam.
Okay. I think the review points out that the test required you study motion, but did you study the
Yes,
motion?
through this hysteresis curve.
I mean, how it moves, how much time it takes to go up and then back.
Yeah, so we use tracker to plot its position over time, the graph of position over time. And then we also have the force over time. So if we combine these data together with for the same time, we can get the position over force.
Did you
Yes, we did do it after, because only this can explain the hysteresis curve. And this is what relates to our theory.
now say you want to check experimentally that the oscillation, the stable points, those two, they have a characteristic frequency, right?
Frequency?
At a stable equilibrium, there is only a minor deviations from that position.
Oh, yes.
Measurement. But did you observe the frequency experimentally?
I think
check
that
with your theory.
but our theory can state about the oscillation in the stable points.
So that's what
Because the stable points are only just to show like the value
that's
of y and
that's
x.
the theoretical formula. Everything follows from that full formula you see first time. But for a physical study, you should have experiments to check whether your assertion, theoretical assertion is correct. And one way to check that is that say for example, the restoring, but we say when it's a minor deviation from the experiment point, it always a simple harmonic motion.
Yes.
And there's a frequency. That frequency is related to its mass and also the spring constant.
Yes.
That effective spring constant. And that should not be checked to see if your theoretical assertion is correct.
Or sure you didn't state simple harmonic motions.
Because the theory, that's theory. I mean,
The
It's
theory
true.
didn't talk about this.
you didn't put it, right?
Yeah, because the theory didn't talk about simple harmonic motion. Yes,
You
but
observe
there
the
is-
existence of stable equilibrium. You have a point at y star, your y star, right? At that point, near that point, you should have observed oscillation, right?
Well, of course, in our experiments, there will be oscillation for stable points.
My point is that there will be, it's different. I observed. Should that, you don't.
So let's start the argument.
No, this is not argument. It's just that I want to know if they did it.
Yeah.
So you answer it, yes or no, you say no, right?
We do observe that we can show you this presentation. So,
So now let's go on to the next question.
Is spring hysteresis linear or non-linear phenomenon?
I think it's linear because it can be predicted from the theory equation. At which point, to which point it will happen.
And then how do you explain the up two points on the same line? You can see from your chart.
This is because so this line and this line are two different directions.
You have the same x value, right? With a root line and root line. You
Yes.
have the same x.
Yes.
So why you have two different y values but the same x value?
Because the direction is different.
This called nonlinear system.
Also, you define nonlinear as.
This is nonlinear system.
Okay, then if this is a linear, I think that this is nonlinear.
And near the point, with a very small deviation, it approaches to the linear system graph the user as. Okay?
Okay.
Is that?
That's
We
all.
have to
Yes.
check the mean.
I'm gonna see. So let's the score for the recorder X77X. And the score for the opponent 75656. And the score for the reviewer X657X. So thank